going to discuss about crystal field splitting in square planar complexes. We have discussed crystal field splitting in the octahedral complex and tetrahedral complex. Now we are going to discuss in square planar complex. In square planar complex means how many ligands will approach to metal is very important. 4 ligands will approach. Of course, in tetrahedral also 4 ligands only will approach, but the way of approach is different here. In this particular square planar complex, the ligands will approach the metal through x and y axis. Example, if you are considering what to call octahedral, so called octahedral there is a z axis also, right? In this z axis, if you are removing these 2, then that will become a square planar complex. In square planar complex, 4 ligands approaches the metal ion through x and y axis, right? And depends on the arrangement of the ligands, the splitting depends, splitting varies. How the splitting varies, now we will discuss, right? In this particular square planar complex, so it is a complex which is somewhat related to octahedral. That means in octahedral we will consider z axis, in this one we will not consider z axis, and so x and y axis only we will be considering here in this particular square planar complex. The x axis ligands experiences a higher crystal field splitting than y axis ligands. If as they are approaching to x and y, right, x experiences more than y. That is very important point to be noted based on the from the square planar complexes. And moving on to this particular one, based on this one, I already we just now we mentioned that xpx whichever is having whichever ligands are moving towards metal ion through x axis, right, that experiences more repulsions compared to y axis. Based on this, what happens? This results in a higher energy for the x axis orbitals and a lower energy for the y axis orbitals. That means x, whoever is lying in x axis, right, their energy will rise. Whoever is lying in y axis, their energy will be down compared to x axis. Obviously, whoever is lying on z axis will come down to that one, right. So, this is the point to be noted here, and moving on to the splitting. Now, let us look at the crystal splitting. Already we have discussed that first at the before that ligands are approaching the metal, it will be in the degenerate state. It will be in the degenerate state. Once after the ligands approaching the metal, the energy rises, still there also the energy will be equal. That is called degenerate state. Just like square tetrahedral or octahedral, here also the content is same. So here dxy, dyz, dzx, dx square minus y square, dz square, the same way. Now when the ligands are approaching the metal ion, what happens in the square planar complex? But square planar complex, directly I am writing square planar complex here, I am not comparing with what so called octahedral. So what happens? The one which is having dx square minus y square, right, that energy will be more here. Why? Because already we mentioned that in square planar complex, the ligand approaches the metal, through which axis? X and y axis. Obviously, x experiences more repulsions compared to y, that also we discussed, but x and y is important. So, dx square minus y will be the orbital which is going to have higher energy. Then which orbital among this one is going to have xy, dxy. So, dxy will come here. Next, moving on to next orbitals, dz square, dyz, dzx. dz square, dyz, dzx. These both will have equal energy. So, this is the way the splitting of orbitals takes place in square planar complex. Square planar complex. Again, square planar complex. Again the splitting varies with respect to metal also, that we will discuss later, but the general splitting is going to be like this. We will have a doubt, dx square minus y square is okay because it is approaching towards x and y. Dxy is okay, then why dz square is somewhat above to this one? It is based on the metal. For example, this type of splitting will happen to the examples like cobalt plus 2, copper plus 2, nickel plus 2, Az plus 2 or Az plus 3, etc. So, for the complexes which are having metal ions like cobalt, copper, nickel, Az, silver in the plus 2 state and silver in plus 3 state, for these complexes the splitting is going to be in this way. In case of platinum and palladium plus 2 state, this dz square will come down, whereas dyz or dzx will go up. The remaining two will be like that, because in square planar complex already we discussed that x and y will experience more. Only difference will come when between these two only. Now let us calculate. Let us know how much splitting energy, crystal field splitting energy we have discussed, right? It will split. Now the overall splitting became how much? That's what you have to know. Now moving on to this one. For example, the splitting happened from here to here. Right? Now the splitting from here to here, delta 3 is how much? 0.00.086 delta naught. Whereas here 0.06 delta naught. Whereas here delta naught. These all are the splittings. And so the overall splitting of delta SP, that is splitting in a square planar complex, is equal to delta 1 plus delta 2 plus delta 3. How much is equal to, how much is going to be? It's going to be 1.746 delta naught. This splitting square planar splitting for which examples we already discussed in the previous slide? Cobalt, copper, nickel plus 2 and Az plus 2, etc. For these one, delta Sp is going to be 1.746 delta naught. What about for platinum and palladium plus 2? That is going to be like this. So here, if you are looking carefully right here, so compared to the previous one, the dz square came down here. This is for the complexes which are having platinum and palladium. For these two, the delta N1, delta 2, delta 3, if you are mixing all together, that is equal to delta Sp, delta 1 plus delta 2 plus delta 2, 3, it is going to be equal to 1.30 delta naught. So in both the examples, whatever may be, whether it is platinum, palladium or nickel, cobalt, copper, whatever may be, delta Sp is going to be the greater than delta naught. That's we have to note it here very importantly. Here what we have to note, now I am going to compare the splitting pattern of octahedral, tetrahedral and square planar. Why? Because we have discussed all these three, right? Which is having high splitting, which is having low splitting, which is having minimum splitting or average splitting. Compared to both, we have to must compare with the diagrams. Now I am going to compare the splitting pattern, splitting of d orbital in all orbitals. In orbitals in octahedral, tetrahedral and square planar, and comparison also. Already we have discussed that the splitting is going to be in octahedral, the splitting is going to be, directly I am writing the splitting only because this is barrier center, we have discussed in the previous slides, right? This is barrier center. Here it is going to be d x square minus y square dx square minus y square and dz square. In this one, it is going to be dyxy, dyz, dzx. This is going to be how much more? Delta naught. This is going to be delta naught. So this is going to be octahedral splitting. Whereas the same splitting in tetrahedral, we already discussed that the tetrahedral splitting is different from the octahedral because it will the ligands will approach the metal ion between the axis. Here it is through the axis. It is the through the axis or along the axis. It is along the axis. It is between the axis. Between the axis. And so what happens? Whoever is between the axis, that is dxy, dyz, dzx, will experience more, and dx square minus y square, dz square will experience less repulsions, and it is going to be how much? Delta naught. Sorry, delta t. This is delta t. This is going to be delta naught. We already discussed that delta t is greater than delta naught is greater than delta t. Why? Because 6 ligands are approaching here and 4 ligands are approaching here. And here it is going to be tetrahedral. And now we are going to discuss about say compare with respect to square planar. In square planar, it is going to be d x square minus y square, d xy, and then d z square, and then d xy, dyz, and dzx. Here if you are comparing, it is going to be delta sp. Just now we have discussed delta sp is equal to how much? 1.746 delta naught. From this one, it is very clear that delta sp is greater than octahedral. So this conclusion we must keep in our mind, because this one can come under very important question as which is highest splitting, which is having highest splitting. Square planar will come under highest splitting, then octahedral, then tetrahedral. In this way we can compare the splitting of the orbitals in square planar, octahedral and tetrahedral. Now let us discuss about one example in the square planar complexes. Right? Square planar complex, I am going to take one example from so many examples. One example I am going to take, that is called nickel cyanide 4 and 2 minus is a charge. Right? Before going to this example, we must know the application of these particular square planar complexes also. These are the complexes which are used in the catalysis as sensors. Right? And also as sensors also we will be using it. Now let us take the example of nickel tetracyano ion actually, right? Nickel right. So tetracyanoniclate is the name of this complex. Now in this complex we are going to discuss about the splitting pattern. What this complex is going to be. Now in this one is very clear that nickel is going to be in the +2 oxidation state. I hope all of you know how to calculate the +2 oxidation state, because nickel is going to have 3d8 4s2 configuration. If you are calculating the oxidation state here, right, x plus 4 into minus 4 minus is equal to -2. From here x will come as how much? +2. In this way we can calculate the oxidation state of nickel in the complex. Nickel +2 means 3d8 is the configuration, right? So 3d8, nickel +2 3d8 configuration I am writing here. 3d8 means how much? D 1 2 3 4 5 1 2 2 3 4 5, right? D8, right? 6 7 8. Now this is the 3d8, 4s0, right, 5p, right, 4s0 and 5p, 3d or 4p, yeah, exactly, 4p is the, now here d8 already it came. Now we are going to discuss about strong complex. What is the meaning of strong complex? A strong field depends on ligand. Strong field here is going to be cyanide. Cyanide is going to be strong field. So this cyanide is going to be strong field, and so what happens? The pairing occurs when splitting occurs, right? And the splitting occurs as it is strong ligand, and pairing occurs before splitting. For example, if you are splitting, right, what happens? 1, 2, 3, right, and pairing also occurs like this. The last electron will come to pair, in this way it will come to pair. Now what happened? Pairing occurred. That means one d orbital will become, after pair happens, the d8 configuration will become like this. 1, 2, 3, 4, 5, 6, 7, 8, and this is going to be empty d orbital, and this one is going to undergo hybridization as shown here. D, the ligand electrons will enter this d orbital, d, s, and this 1, 2 and p2. So the overall configuration is going to be d, s, p plus p. Overall hybridization is going to be dsp2. dsp2 means it's going to be square planar complex. What complex is going to be? Square planar complex. So the splitting already we have discussed. The splitting will happen in this way only. X square minus y square, xy, z square, yz, zx. In this only splitting happens in this nickel case. So this is, in this example, cyanide is a strong ligand. Formation of square planar complex geometry is very clear in this geometry. And overall, if you want to look into the overall structure, right? So nickel complex will have 4 ligands like this: cyanide, 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 and overall complex is going to be -2. Right? This is the square complex, square planar complex, and with this square planar complex, with this we have completed the splitting pattern of octahedral, tetrahedral, and square planar complexes.